Between the galaxies there are holes, not gaps. Holes. Some stretch over 1 billion light-years across, containing almost nothing. No stars. No gas. No light. We call them voids, and they make up most of the universe you live in. Tonight, you'll travel to a bubble of nothing that may be swallowing our galaxy, a void so cold it broke physics, and a region where time itself seems to stretch. If cosmic mysteries keep you up at night, hit subscribe and stay close. Dim the lights. Settle in. We begin. Step outside on a clear night. Look up at any patch of sky between the stars. What you cannot see is the thing that should terrify you most. Our galaxy sits at the edge of something astronomers call the local void. It begins just beyond our cosmic neighborhood and stretches outward for about 150 million light-years. Inside this region, there is almost nothing. No bright galaxies, no glowing gas clouds, no companions for any traveler who might wander in. For decades, scientists assumed the universe was filled evenly with galaxies, like raisins scattered through a cake. The reality is far stranger. Galaxies cluster along thin threads of matter, and between those threads, vast empty rooms stretch open. Our Milky Way is pressed against the wall of one of those rooms. A team led by astronomer Brent Tully made this discovery in the early 2000s. They mapped the motion of nearby galaxies and noticed something unsettling. The galaxies were not just moving outward with the expansion of space, they were being pushed away from a specific direction, as if shoved by an invisible hand. That hand was the local void. Empty space sounds harmless. Empty space is anything but. The void has gravity, or rather, the absence of gravity that surrounding matter feels. Galaxies on the edge of a void are pulled toward denser regions and away from the empty zone. Our galaxy is being pushed by the local void at roughly 260 kilometers every second. That force is real. That force is happening to you right now. Picture standing on a tiny island in the middle of a black ocean. The water has no waves, no currents you can see, no sound. But the island is drifting, slowly, steadily, toward a distant shore you cannot identify. That is where we live. Here is the part that gets stranger. The local void may be even bigger than we thought. Recent surveys suggest its true edge extends much farther than the original maps showed. Some galaxies, once believed to be inside our cosmic neighborhood, actually sit on the far rim of this emptiness. The void has been hiding parts of itself behind the bright glare of nearby stars. Inside the local void, there are still a few small galaxies. They are dim, scattered, and impossibly isolated. If life existed on a planet inside one of those galaxies, the night sky would look almost dead. Only a faint smear of distant light, separated by oceans of black, would mark the rest of creation. No Andromeda, no Magellanic Clouds, just darkness in every direction. This raises a question that haunts cosmologists. If our galaxy was born so close to the edge of such a vast emptiness, did the void shape us? Did its strange gravity decide which stars formed, and which never had a chance? Some researchers now believe the Milky Way's history was bent by the presence of this void, like a tree growing crooked because of the wind. The local void is the closest cosmic emptiness to your bedroom window. It is also the smallest one we will visit tonight. Far beyond our local emptiness, in a constellation that ancient skywatchers called the Herdsman, lies something that should not exist. A hole so massive, it once made astronomers question whether their telescopes were broken. In 1981, a young astronomer named Robert Kirshner was mapping galaxies in a slice of sky toward the constellation Borealis. He expected to find the usual clusters and threads. Instead, he found nothing. For page after page of data, the count of galaxies dropped to 0, then dropped again, then stayed at 0 across an area so wide it seemed impossible. Kirshner and his team checked their equipment, they checked their math, they checked the photographic plates. The emptiness was real. What they had stumbled into was a hole in the universe roughly 330 million light-years wide. To put that in perspective, light leaving one side of this void today would not reach the other side until long after the human species had vanished from Earth. If you shrank our entire galaxy down to the size of a marble, the Borealis void would be the size of a major American city. Inside it, almost nothing. surveys eventually found around 60 galaxies scattered across the entire region. 60. In a volume that should have held tens of thousands. The galaxies that do exist there are spread so far apart that each one stands utterly alone in the dark. Imagine being on a planet inside one of those lonely galaxies. You look up. The sky has no Milky Way band stretching across it, no companion galaxies hanging like lanterns nearby. The nearest neighbor galaxy is so far away that even with the strongest telescope, it looks like a single dim smudge. For most of human history, your astronomers would believe their galaxy was the entire universe. There would be nothing else visible to suggest otherwise. The Borealis void changed cosmology overnight. Until that point, scientists believed matter in the universe was distributed in a smooth, fairly even way, with small variations. A void this large violated that idea completely. The math said voids of this scale should not have had time to form since the Big Bang. The universe was not old enough. Yet, there it was. Researchers began searching for explanations. One theory proposed that the Borealis void was actually several smaller voids that had merged, like soap bubbles joining together when they touch. Another suggested that early ripples in the infant universe had been larger and more dramatic than anyone realized. A third, more unsettling idea was that our understanding of how matter clumps together was simply wrong. Kirshner himself once described the discovery with quiet astonishment. He said it felt like opening a door in a crowded house and finding a hallway that led to a cathedral with no one inside. The image stuck. Astronomers still use it. Now consider this. The Borealis void is not the only one. Surveys since the 1980s have revealed that voids of this scale are scattered throughout the observable universe. They are not rare anomalies. They are the norm. Most of the volume of space is empty in this way. The bright threads of galaxies you see in cosmic maps are the exception, not the rule. You live in a universe that is mostly nothing. The somethings are the strange exceptions. That truth sounds simple. Following it to its logical end is where the nightmare begins. To understand how we ever found these voids in the first place, we need to go back to a stack of computer printouts in the 1970s, where a team of scientists nearly missed the biggest discovery in modern cosmology. Before the late 1970s, almost no one believed in voids. The universe was supposed to be smooth. Galaxies were thought to be sprinkled through space the way salt is sprinkled across a tabletop. Plenty of variation up close, but step back far enough and the distribution looked even. Then came redshift surveys. A redshift is a measurement of how fast a galaxy is moving away from us. The faster the motion, the farther the galaxy. By measuring redshifts for thousands of galaxies, astronomers could finally build a real three-dimensional map of the cosmos. Before this, all maps had been flat, like looking at lights in a city window without knowing how far back each one stood. In 1978, Stephen Gregory and Laird Thompson published a paper that began to change everything. They had been studying a particular cluster of galaxies, called the Coma supercluster. While charting it in 3 dimensions, they noticed empty regions on either side, big ones, larger than the cluster itself. At first, the gaps were treated as oddities. Then, as more redshift surveys rolled in, the gaps started showing up everywhere. Gregory and Thompson had found the first hint of voids, and they had found them by simply asking a better question. Not how many galaxies are out there, but how are they arranged? The breakthrough kicked off a frantic decade. Teams across the world began racing to map the sky in depth. The most famous of these was the Center for Astrophysics survey, led by Margaret Geller and John Hutchrer at Harvard. Their work produced an image that has since become iconic in the field. A wedge-shaped slice of the universe, dotted with galaxies, showing clearly that those galaxies were arranged in vast filaments and walls, with enormous empty regions between them. When that map was first unveiled at a conference in the 1980s, the reaction was something like stunned silence. Cosmologists had expected a uniform speckle. What they got was a structure that looked like sea foam, or like soap suds in a sink, bubbles of nothing pressed against bubbles of nothing, with galaxies clinging to the thin walls between them. The map was nicknamed the Stickman because one cluster of galaxies, by sheer coincidence, looked like a tiny human figure inside the foam. Behind that figure stretched the Borealis void. The Stickman stood at the edge of an abyss. Geller put the discovery in plain terms in interviews. She said the universe was not filled with galaxies. It was mostly empty, and the galaxies were the exceptions, the small, bright outlines around vast nothing. Hearing her describe it, you can feel how strange the realization must have been. An entire field of science had to flip its mental picture of reality. What makes this story unsettling is how close we came to missing it. Without redshift surveys, voids would have stayed hidden in plain sight. Looking at the night sky with the naked eye, or even with most telescopes, the universe still appears full. The emptiness only reveals itself when you measure depth. That raises a question worth sitting with. If the largest features of the cosmos hid from us until just a few decades ago, what else is still hiding? The answer to that lies in a structure too vast to be called a thing, a network, a web, a pattern that connects every galaxy you have ever heard of, and explains why voids must exist at all. If you could shrink the entire observable universe down to the size of a basketball and look at it from outside, you would not see scattered points of light. You would see a tangle, a vast, lacy structure of glowing threads, some thicker, some thinner, all connected. Between those threads, bubbles of emptiness. This is the cosmic web. The web is real. It has been mapped. It is the largest known pattern in nature. Galaxies are not floating freely. They are strung along filaments of dark matter like beads on a necklace. Where filaments cross, galaxies pile up into massive clusters. Where filaments thin out and disappear, voids open up. The bright web and the empty bubbles are two halves of the same structure. You cannot have one without the other. To understand why, picture the early universe. Soon after the Big Bang, matter was spread out almost evenly, but with tiny ripples in its density. Some regions were a hair denser than average. Others were a hair thinner. These differences were small, microscopic on cosmic scales. Gravity is patient. Over billions of years, the dense regions pulled in more matter from their surroundings. Their gravity grew. They became denser still, attracting even more material. Meanwhile, the regions that had started slightly thinner lost matter to their richer neighbors. They emptied out. They kept emptying. Run that process for nearly 14 billion years, and you get the cosmic web. The dense seeds became filaments and clusters. The thin seeds became voids. Every void you have ever heard of started as a slightly emptier patch in the early universe and slowly drained itself. The numbers here are hard to picture, so try this. Imagine a sponge. Most of the sponge is air. The solid material is just the thin walls between the holes. The cosmic web works the same way. Most of space is hollow. Galaxies live in the walls. Computer simulations have confirmed this picture in stunning detail. When researchers feed the laws of gravity and the early conditions of the universe into a supercomputer, the cosmic web emerges naturally. The simulated universe ends up looking almost identical to the real one, foam and all. That match is one of the strongest pieces of evidence that modern cosmology is on the right track. There is something deeply unsettling buried in this discovery. The cosmic web is held together by dark matter, an invisible substance that we have never directly detected. Roughly 5 times more dark matter exists than the regular kind that makes up stars and planets. The galaxies you can see are riding along inside vast halos of stuff no human has ever observed. The web you live on is largely made of something nobody can identify. That mystery has a flip side. If dark matter shapes the threads, then the voids are the regions where even dark matter has thinned out. They are not just empty of stars and gas. They are the most genuinely empty places in the universe, made of the least amount of everything we know. This brings us to a strange consequence that nobody expected. Inside these vast empty regions, the few galaxies that manage to form do not behave the way galaxies elsewhere do. They are different. They are quieter. And in some ways they appear to be aging at a different speed than the rest of the universe. A galaxy in a cluster lives a violent life. It collides with neighbors. It steals their gas. It triggers waves of star formation when it passes too close to another disk. Its history is full of mergers, near misses, and gravitational scars. A galaxy inside a void lives almost completely alone. For billions of years, a void galaxy may have no significant neighbors close enough to disturb it. No collisions, no gravitational tugs strong enough to matter. It drifts through empty space, doing whatever it does, untouched by the chaos that defines the rest of the cosmos. This isolation has a measurable effect, and it shows up in the data in ways that surprised astronomers. Void galaxies tend to be smaller than average. They tend to be bluer, meaning they are still actively forming new stars, while many cluster galaxies have run out of gas and gone red. They tend to spin in slower, calmer patterns. They look in many ways younger. Younger is the key word. A galaxy in a busy cluster has often used up its gas reserves quickly, in furious bursts of starbirth triggered by collisions. By the present day, many cluster galaxies are old and quiet, with little fuel left. Void galaxies, by contrast, have had no neighbors to wake them up. Their gas has been sipped, not gulped. They still have material left to make new stars, even now. That sounds peaceful. The reality is unsettling. Researchers who study void galaxies sometimes describe them as if they exist on a delayed cosmic schedule. The rest of the universe is moving on, growing old, settling down. The void galaxies are still in their adolescence. They behave like the universe of several billion years ago, frozen in slow motion, because nothing has come along to disturb them. That delay is real. It can be measured in the colors of their stars, in the rates at which they form new ones, in the structures of their disks. A void galaxy is, in a sense, a window into the past, still open in the present. Picture two children born on the same day. One grows up in a packed neighborhood, full of fights, friendships, and constant activity. The other grows up alone on a quiet farm, with no one nearby for miles. Decades later, you visit them both. The first looks worn, marked by every encounter. The second looks oddly unchanged, as if life had passed more gently. Now scale that idea up to galaxies, and you have a sense of what voids do. Some astronomers have begun to wonder whether intelligent life would have a different story in a void galaxy. Stars there might burn for longer in calm orbits. Planets might survive without being sterilized by nearby supernovae or galactic collisions. The brutal reshuffling that happens in dense neighborhoods would be absent. In theory, a void galaxy could be one of the most stable cradles for long-lived civilizations in the entire universe. In theory. Because there is a flip side. A civilization born inside a deep void would face a special kind of horror. Their sky would be almost empty. The nearest galaxy to study, the nearest cosmic landmark, the nearest possible neighbor would all be hopelessly far away. They would not just be alone. They would be alone in a way that nothing on Earth has ever truly experienced. One known galaxy makes that loneliness real. A real galaxy. A real silence. A name worth remembering. In the constellation of Pisces, deep inside a vast cosmic emptiness, there is a galaxy with no friends. Its catalogue name is MCG plus 01020015. It is a quiet spiral, not unlike our own Milky Way in basic shape, though smaller and dimmer. It sits inside a region known to astronomers as a great void, surrounded by tens of millions of light years of nearly empty space in every direction. Its nearest galactic neighbor is roughly 100 million light-years away. To translate that distance, consider this. From our galaxy to the Andromeda Galaxy, the most famous nearby spiral, is about 2.5 million light-years. That gap is already so wide that a beam of light leaving Andromeda when human ancestors first began walking upright would still be in transit today. Now multiply that gap by roughly 40. That is how isolated MCG plus 01020015 is. If life ever formed on a planet orbiting a star inside that galaxy, its sky would be one of the strangest in the cosmos. There would be local stars, of course. Constellations of a kind. The faint band of the home galaxy stretching across the night, much like our Milky Way appears to us. But beyond that band, the rest of the universe would look almost completely dead. No glowing companion galaxies. No bright clusters tempting future telescopes, just a black expanse with the merest whisper of distant light, and only to instruments far more sensitive than anything we have yet built. Astronomers studying MCG plus 01020015 have called it the loneliest galaxy in the known universe. Some have written about it with a strange tenderness. One paper described it as a galaxy that does not even know how alone it is, because the light from its nearest neighbor is too faint and too old to have any meaningful effect on it. What makes this story sharper is that the galaxy is not unusual in any other way. It looks ordinary. It does ordinary galactic things. It forms stars, holds planets, presumably hosts solar systems. The only extraordinary thing about it is its address. It happens to live in the wrong neighborhood, a neighborhood with no other neighborhoods nearby. Now picture what a civilization there might believe. Without the constant context of nearby galaxies, the people of that world would have no easy evidence that the universe is full of structure. Their telescopes would have to be vastly more powerful than ours just to detect the existence of other galaxies at all. For centuries, even after they invented optics, their best astronomers might still teach that their galaxy was the entire universe. The truth would be hidden behind a black wall of nothing. That thought is more than a story. Some cosmologists have argued seriously that civilizations inside deep voids would face a permanent handicap in understanding reality. The clues we use on Earth, the bright neighbors, the obvious cosmic patterns, would not be there to guide them. Their cosmology might be built on a much smaller, lonelier picture, and they would have no easy way to know they were wrong. MCG plus 01020015 raises a haunting possibility about distance itself, because there is something inside voids, something nobody can see and nobody can touch, that may be making them grow faster than space itself. The universe is expanding. You have heard that line so often it almost loses meaning. Galaxies fly apart, distances grow, space itself is stretching. What you may not have heard is that the expansion is not happening evenly. Inside the cosmic voids, space stretches faster. This is one of the strangest discoveries of modern astronomy. The empty regions of the universe are not just sitting there, frozen in their emptiness. They are inflating, pushing outward, growing larger every second, and the engine driving them is the most mysterious force ever discovered. That force is called dark energy. Dark energy was identified in the late 1990s when two separate teams measured the brightness of distant exploding stars and realized something was off. The universe was not slowing down the way gravity should have demanded. It was speeding up. Some unknown energy was pushing space apart and pushing harder over time. Today, dark energy is believed to make up roughly 70% of all the energy in the universe. The biggest ingredient of reality is something we cannot detect directly and barely understand. Inside a galaxy or a cluster, gravity holds everything together. Stars, planets, dust, dark matter, all bound by their own pull. Dark energy still tries to push them apart, but locally, gravity wins, so nothing about your daily life is being torn apart by it. Yet, inside a void, the story flips. There is too little matter to fight back. Dark energy works almost unopposed. The void inflates, grows wider, and the few galaxies on its rim get pushed outward faster than the average expansion of space. From the perspective of those galaxies, the void is hollowing itself out, becoming emptier, becoming bigger. Picture a foamy ocean of soap bubbles. Each bubble represents a void. Now imagine that the air inside each bubble keeps pushing outward, while the soap walls only shift slowly. Over time, the bubbles swell. The walls between them, where the galaxies live, get squeezed thinner. The cosmic web is being stretched, slowly but relentlessly, by a force nobody can see. The implications are heavy. Voids are not just leftovers from the early universe. They are active. They are growing. The universe is becoming more void over time, not less. If this trend continues for hundreds of billions of years, the bright structure of the cosmic web will thin out to almost nothing. Galaxies and clusters will stand on shrinking islands surrounded by ever larger oceans of emptiness. Astronomers sometimes describe this as the long-term fate of everything. In the deep future, every galaxy outside our own gravitationally bound neighborhood will be pushed beyond the cosmic horizon. Their light will redshift away into nothing. Future astronomers, if they exist, will look up at a sky that contains only the Milky Way and its closest companions. The rest of the universe will be invisible. The voids will have won. That sounds like a problem for the distant future. It may also be a problem for the present. Some cosmologists have argued that we, the people on Earth, may already be sitting inside one of these growing voids. Not on its edge, not nearby. Inside it, a bubble of below-average density that could be skewing every measurement we make about the cosmos itself. If that is true, the consequences are unsettling. In 2013, 3 astronomers, Ryan Keenan, Amy Barger and Lennox Cowie, published a study that would unsettle their entire field. They had been measuring the density of galaxies in our cosmic neighborhood out to extremely large distances. The result was strange. The region around our Milky Way was emptier than expected. Not just locally, across a sphere roughly 2 billion light-years wide, centered roughly on us, the average count of galaxies was lower than what the rest of the universe shows. Significantly lower. About half as dense. This region became known as the KBC void, named after its discoverers. If the measurement is correct, it is one of the largest known structures in the universe, and we live near its center. Let that picture settle. Our galaxy may not just be near a void, it may be inside one. A vast, underdense region stretching for 1 billion light-years in every direction, with the rest of the universe sitting out beyond its walls. This idea is controversial. Many cosmologists are uncomfortable with it because of a long-held principle in their field. The universe, they assume, should look roughly the same from any vantage point on large enough scales. We should not be in any special location. A void this huge, with us near the middle, would suggest an unusual arrangement. The data, however, keeps showing the same thing. Galaxy counts thin out as you measure outward from us, then rise again at extreme distances. The shape of the local universe matches a void. There is more. The KBC void may quietly be solving one of the biggest puzzles in modern astronomy, the so-called Hubble tension. Here is the puzzle in plain terms. Astronomers measure the expansion rate of the universe in two main ways. One method uses nearby galaxies and exploding stars. The other uses the faint glow left over from the Big Bang, called the cosmic microwave background. Both methods should agree. They do not. The two values are different by several percent, a gap that has refused to close for a decade. Something is wrong. Either the measurements are off, or the universe is. If we live inside the KBC void, the two values can be reconciled. Inside an underdense region, dark energy works more aggressively, and the local expansion looks faster than the average. Our nearby measurements would naturally come out higher than the cosmic average measured from the microwave background. The tension would not be a flaw. It would be a clue. A study published in 2020 by Indranil Banik and his collaborators argued exactly this. They modeled a universe in which our galaxy sits inside a giant void, and the numbers came out far closer to the observations. Other researchers remain skeptical. The debate is alive and the data keeps refining. What makes this so heavy is the implication. If we really live inside such a void, then almost everything we have measured about cosmology has been distorted by our local environment. Like a fish in a deep pool, judging the entire ocean by the temperature of its water, the walls of this void, if they exist, are far beyond anything humans will ever visit. But the walls are not the only thing inside that distorts our view. The light itself behaves strangely there. Light is supposed to travel in straight lines. In a perfect, empty universe, it would. But the universe is not perfect, and light has to pass through regions where gravity warps the very space it moves through. This effect is called gravitational lensing, and it is one of the most useful tools astronomers have. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends the path of that light, sometimes splitting one image into multiple copies, sometimes stretching the galaxy into long arcs. The bigger the mass, the bigger the bend. Voids do the opposite. When light enters a void, there is less mass than average around it. Space inside the void is, in a sense, less curved than the average region. Light passing through a void does not bend toward gravity. It bends away from emptiness, in a subtle reverse effect that astronomers call anti-lensing or void lensing. The signal is faint, easy to miss. It took years of refinement before researchers could measure it cleanly. By 2012, surveys were detecting it confidently. Galaxies seen through voids appeared slightly less stretched than the cosmic average, and the pattern matched theoretical predictions for what underdense regions should do. This confirmed something important. Voids are not just statistical patterns in galaxy maps. They are real gravitational features, real regions where the geometry of space behaves differently. You can see their fingerprints in the light passing through them. There is a stranger effect too, called the integrated Sachs-Wolf effect. Light from the early universe, the cosmic microwave background, has been traveling for nearly 14 billion years to reach us. Along the way, it has crossed countless voids and clusters. Each crossing leaves a small mark on the temperature of that ancient light. Light that passes through a growing void loses a tiny fraction of its energy, arriving slightly cooler. Light that passes through a growing cluster gains a tiny bit, arriving slightly warmer. In 2008, researchers compared maps of cosmic voids with maps of the microwave background and found the predicted pattern. The coldest patches in the ancient light tended to align with the deepest voids. The slight excess heat lined up with major clusters. The cosmic web had been imprinting itself on the oldest light in the universe, and we could read it. Picture a stream flowing across a landscape. Wherever there is a hill, the water flows around it. Wherever there is a valley, the water dips in and rises again on the other side, slightly slower than before. Light crossing the cosmic web does something like this. Voids are the valleys, clusters are the hills. The light arrives carrying a record of every dip and climb. This means the voids leave traces in everything we see, not just in galaxy counts, but in light bending, in temperature maps, in the shapes of distant objects. They are not invisible. They are merely subtle, and once you know how to look, the universe is full of their fingerprints. That brings up a darker thought. If voids can imprint themselves so widely on the universe, what could a truly enormous void do? Not one of the average voids in the cosmic web, but something far larger, far stranger, something that may already be visible to us, and that we still do not understand. A region of sky known to astronomers simply, ominously, as the cold spot. In 2004, the Wilkinson Microwave Anisotropy Probe, a satellite designed to map the oldest light in the universe, sent back something that did not fit. In a region of sky toward the constellation Eridanus, the cosmic microwave background was unusually cold, much colder than the average, colder than statistical models said it should ever be. This patch of sky became known as the cold spot. The cold spot covers a vast area roughly 5 degrees across, 10 times the apparent size of the full moon. Its temperature is only about 70 microkelvins below the cosmic average. The number sounds tiny. In the language of cosmology, it is enormous. The probability that such a chilled patch could appear by random fluctuation is very low. Something seemed to be there. Something was making the early light colder. The first idea was that the cold spot might be an imprint of a giant void. Light passing through a vast underdense region would lose energy as it traveled, arriving slightly cooler at our telescopes. If the void were big enough, it could leave a chilled stamp on the microwave background. Searches began. By 2015, a team led by Istvan Sapudi and Andras Kovacs reported they had found a candidate. They named it the Eridanus supervoid. Their estimates put it at roughly 1.8 billion light-years across, sitting at a moderate distance from us, aligned with the cold spot in the sky. If their measurement holds up, the Eridanus supervoid would be one of the largest known structures in the universe. The numbers strain belief. A region nearly 2 billion light-years wide, far emptier than its surroundings, big enough to leave a cold scar on the oldest light we have. The story did not stay clean. Other researchers have since argued that the Eridanus supervoid, even at this size, is not enough to fully explain the cold spot. Their calculations suggest a void that big would only chill the microwave background by a fraction of what is observed. The math leaves a gap, a small, unsettling gap. That gap has invited more exotic explanations. Some cosmologists have proposed that the cold spot might be a bruise, a scar left by a collision between our universe and another one in a multiverse picture. In that scenario, our entire cosmos has bumped against a neighboring bubble universe at some point in its history, and the cold spot is the mark left behind. The idea sounds wild, but it has been published in respected journals because conventional explanations do not fully fit. If the supervoid is not enough to explain the temperature drop, something else has to make up the difference, and nobody knows what. Picture an ice rink that is freshly polished and almost perfectly smooth. Across most of its surface, the temperature is steady. In one corner there is a patch that is colder than it should be. You measure the floor, the ceiling, the airflow. Nothing accounts for it, yet the cold is there every time you check. That is the cold spot, scaled up to a region millions of light-years wide. The cold spot remains one of the most discussed anomalies in modern cosmology. The Eridanus supervoid is the leading explanation, but it might not be the full one. And if the rest of the answer is something stranger, it would force us to consider a possibility most physicists prefer not to discuss, a possibility that lives quietly in the math of the universe: waiting. The idea sounds like fiction. The math says otherwise. In some versions of modern cosmology, our universe is not the only one. It is one of many bubble universes inside a far larger structure, sometimes called the multiverse. Each bubble has its own laws, its own history, its own clock. Most of them never touch each other. The space between them grows too quickly. But not always. If two bubble universes happen to collide while still in their early, rapidly expanding phase, the impact would leave a mark, a bruise on the cosmic microwave background, a patch of sky where the temperature, the polarization, and possibly the density of matter would all be subtly off. Not a scratch, a round, smooth, characteristic dent. This idea was developed by physicists working on theories of cosmic inflation, the moment in the very first split second of the universe when space itself stretched at an unimaginable rate. Some inflation models predict that this rapid stretching never fully ended everywhere. New universes may still be popping into existence, somewhere far beyond what we can see. Most never interact with us. A few, statistically, might have. Now compare that to the cold spot. The cold spot in Eridanus has a roughly circular shape. Its temperature dip cannot be fully explained by the underlying void alone. Its location is unique in the sky. Several physicists, including Tom Shanks at Durham University, have noted that these features match the kind of imprint a bubble collision might leave behind. This does not mean the multiverse has been proven. It is a hypothesis, a serious one, but unproven. Most cosmologists prefer to keep searching for natural void explanations before reaching for something so dramatic. The point is that the cold spot has not been fully accounted for, and the door is technically open. If that door ever fully opens, the implications would shake every assumption you have about reality. It would mean our universe is not unique. It would mean that out beyond the edge of our cosmic horizon, other realities might be expanding alongside us, with their own stars, their own galaxies, possibly their own physics. We would be one of countless balloons in an unseen storm. Picture standing on a beach at night, looking at the ocean. You can only see the water nearest you. Everything beyond a certain distance is invisible. Now imagine that the surface of the water is dotted with bubbles, each one a separate world. Most of them never touch each other because the water keeps them apart. But once in a long while, two bubbles graze each other on the way past. A faint ripple is left behind, a scar in the foam. The cold spot might be such a ripple, or it might not. The honest scientific answer right now is that we do not know. What is striking is how voids and multiverse theories have become entangled. The very emptiness of the cosmos has become a place where the deepest questions about reality are being argued out. The voids are not just holes in the universe. They are pages in a book that may be far longer than anyone realized. Yet to understand how voids could even exist, you have to go back to a moment far earlier than any of this, before galaxies, before stars, to a time when the universe was a hot glowing soup and the only movement was sound. Sound waves so vast they would carve the cosmos. In the first 400,000 years after the Big Bang, the universe had no stars, no galaxies, no atoms in the modern sense. It was a glowing fog of charged particles and photons, packed so densely that light could not travel freely. The whole cosmos was opaque, hot, and pressurized. Inside this fog, sound was possible. When matter clumped slightly anywhere, the radiation pressure from photons pushed back. The clumps oscillated. Each ripple sent out a wave of pressure that moved through the plasma at relativistic speeds. These were sound waves, but on a cosmic scale, vast pulses traveling outward from every dense seed in the early universe. Each sound wave traveled a measurable distance before the universe finally cooled enough for atoms to form. At that moment, around 380,000 years after the Big Bang, the photons broke free, the fog cleared, and the sound waves froze in place. The pattern they had drawn was locked into the distribution of matter forever. This frozen pattern is called a baryon acoustic oscillation. The wavelength of those primordial sounds, stretched by cosmic expansion, is now about 500 million light-years across. Across the entire universe, there is a faint extra tendency for galaxies to be separated by exactly that distance. It is a leftover ringing from the loudest sound in history. Voids fit into this story in a haunting way. Where the early sound waves overlapped destructively, matter was thinned out. Where they overlapped constructively, matter piled up. The cosmic web is, in a real sense, the fossil of those primordial sounds. The bright filaments are the crests of long-vanished waves. The voids are the troughs. You live inside a frozen song. That phrase is not poetry, despite the rules of this script. It is a literal description. The arrangement of galaxies, clusters, walls and voids is the residue of acoustic oscillations from a moment when the universe was hot enough for sound to shape matter. The patterns have been measured. The wavelengths have been confirmed. The cosmos remembers. Picture striking a great drum in a sealed room. The vibrations spread outward, bounce off the walls, interfere, create patterns of louder and quieter spots in the air. Now freeze that pattern in place forever. Replace the air with matter. Let the matter clump where the sound was loud and stay sparse where the sound was quiet. That is, in essence, how the cosmic web formed. There is something deeply unsettling about this picture. It means voids are not random. They are not just statistical thin spots. They are sculpted. Each one of them traces back to a specific overlap of pressure waves in the first 400,000 years of the universe. Every emptiness has a cause that runs through fundamental physics, fluid dynamics, and the cooling of plasma. The map of the cosmos is a record, frozen and stretched, of the universe's first and only true symphony. Astronomers now use these frozen sound waves as a ruler. By measuring how the typical galaxy separation changes with distance, they can chart the expansion history of the universe. Voids and clusters together carry that ruler in their structure, yet inside the deepest voids, the silence is far more extreme than anywhere on Earth. The actual emptiness, atom by atom, is harder to grasp than any laboratory vacuum. When you imagine empty space, you probably picture something close to nothing. The reality inside a void is far more extreme. To set the stage, consider the average density of the universe. Across all of space, on the largest scales, there is roughly 1 atom of hydrogen per cubic meter of volume. 1. Across a box the size of a small refrigerator. That is the cosmic average, and it already feels like emptiness beyond imagination. Inside a void, the density drops further. The deepest voids are estimated to contain between 10 and 20% of the average matter density. In some regions, far less. That means inside the heart of a void, you might find 1 atom in every 5 cubic meters. In others, even fewer. Stretched out, that is a level of emptiness that no engineer has ever produced on Earth. The best vacuum chambers built in modern laboratories reach densities of about 100 million atoms per cubic centimeter. Even those ultra-high vacuums, used in particle physics and semiconductor fabrication, are dense compared to the deep cosmos. To match the emptiness of a cosmic void, you would have to scoop out the contents of an Olympic swimming pool and find perhaps a handful of atoms total. It gets stranger. The atoms inside voids are not just sparse, they are also slow. The temperature of intergalactic gas inside voids is extremely low compared to gas inside clusters, which can reach millions of degrees. Inside voids, much of the gas is cool, dim, and barely emitting any light at all. It is so faint that for a long time astronomers could not detect it directly. Indirect methods, like watching how distant quasar light is absorbed as it passes through the void, finally provided the evidence. The picture this paints is haunting. A cubic light-year of void contains less matter than the air inside a single human breath. Stretch that across 1 billion light-years, and the total amount of stuff is still pitifully small compared to a single galaxy cluster. The universe is mostly nothing, by mass and by volume both. Picture standing in the middle of a desert at night. There is sand under your feet, and somewhere beyond the horizon, cities. Now strip away the ground, strip away the atmosphere, strip away every grain of sand for as far as you can see in any direction. Leave only a single floating dust speck somewhere in your line of sight. That is not yet empty enough. Move that dust speck away by hundreds of miles. Now you are getting close. This kind of emptiness has consequences. Ordinary physical processes that depend on matter interacting do not happen there. Particles cannot easily collide. Fields stretch out unimpeded. Even basic chemistry, the kind that creates molecules, becomes nearly impossible in deep voids because the atoms can drift for vast distances without ever encountering another. For most of human history, the word empty has meant something we could imagine: a glass with no water, a room with no people. The cosmic voids force the word to mean something altogether different. They are emptiness so pure that the laws of physics behave differently inside them. That difference does not stop at density and temperature. There is reason to believe that even time, the most fundamental measurement of all, may stretch in unexpected ways near a void's edge. Time is supposed to be the same everywhere. That is the comforting picture. A second on Earth is a second on Mars, a second in another galaxy, a second at the edge of the observable universe. The truth is more delicate. Albert Einstein showed over a century ago that gravity changes the rate of time. Stronger gravity slows clocks down. Weaker gravity speeds them up. This effect has been measured countless times. Atomic clocks at high altitudes tick slightly faster than identical ones at sea level. Satellites in orbit around Earth must constantly correct for the difference, or their navigation signals would drift. Now extend that idea to voids. A void is a region where gravity is weaker than average, because matter is sparser. Clocks inside a void should, in theory, run slightly faster than identical clocks inside a dense cluster. The effect for any single clock is tiny. Across cosmic scales and cosmic times it becomes measurable. In effect, the deepest voids are running on a slightly accelerated timeline compared to galaxy clusters and the regions in between. This is not a science fiction premise. It is a direct prediction of general relativity, and astronomers have begun finding faint evidence of it in the way distant void galaxies appear to evolve. Picture two travelers leaving Earth on identical clocks. One is sent on a voyage that hugs galaxy clusters and dense cosmic walls. The other is sent on a voyage that crosses long stretches of voids. Even if both travel at the same speed, when their clocks are compared at the end, they will not match. The void traveler's clock will have ticked off slightly more time. The difference is small. The principle is real. Things get stranger near the edges of large voids, where the gravitational gradient between empty space and a galaxy cluster is steepest. In those border regions, the geometry of space-time is more sharply curved than the interior of a void or the interior of a cluster. Light passing through these edges bends. Time passes at slightly different rates on either side of the edge. Some cosmologists have argued that these gradients might be the most physically interesting places in the universe. They are not where matter is densest. They are where the contrast is sharpest. A galaxy on the rim of a void experiences forces and timing differences that a galaxy deep inside a cluster never feels. This has practical consequences for cosmology. When astronomers measure the universe's expansion rate using galaxies near void edges, the measurement is subtly different than when they use galaxies in dense regions. Some researchers have even suggested that part of the Hubble tension, that stubborn disagreement between expansion rate measurements, comes from this effect. Different methods sample different parts of the cosmic web where time and expansion behave slightly differently. If that is true, the universe is not a single ticking clock. It is more like an orchestra, where every region keeps its own slightly drifting tempo. The voids tick a little faster. The clusters tick a little slower. Across billions of years, those drifts add up to noticeable differences in how galaxies grow, age, and evolve. There is one consequence of this strange timing that nobody anticipated. Inside the voids, certain kinds of small galaxies have been found that by every model should not exist at all. They are the wrong size, the wrong shape, in the wrong place. Voids are supposed to be lonely, empty, quiet. Yet inside many of them, astronomers have found something unexpected. Small, dim galaxies. Tiny ones. Sometimes scattered, sometimes paired with even smaller companions. These are the void dwarfs. Dwarf galaxies in general are common across the universe. They are smaller than spiral galaxies like the Milky Way, often containing only a few 100 million stars instead of hundreds of billions. They tend to cluster around larger galaxies, forming small companion systems. Our own Milky Way has dozens of them in orbit around it. The strange thing about void dwarfs is where they are. They are not orbiting larger galaxies. They are not part of clusters. They are inside the voids, far from any major neighbor. By the standard models of how galaxies form, there should not be many dwarf galaxies in such isolated places. Galaxies need dark matter halos to form, and the seeds for those halos are supposed to be rare in low-density regions. The void dwarfs ignore the prediction. They exist in numbers that surprise the models. They form stars. Some of them have unusual properties, like high amounts of cold gas, that suggest they are still actively evolving billions of years into the universe's history. A team led by Catherine Krekel and others has been mapping void galaxies in detail. Their results show a population that is alive, varied, and harder to explain than expected. Some void dwarfs have rotation patterns that hint at strange dark matter distributions. Some sit in tiny groupings of 2 or 3 dwarfs, with no larger galaxy in sight, like small islands stranded together in a vast sea. Picture an Arctic landscape that should be lifeless. You expect ice and silence. Instead, scattered across the ice, you find tiny villages. Not many, not crowded, but there where nothing should support them. The locals have somehow built a working life in a place the map said was empty. That is the feeling void dwarfs give cosmologists. These small galaxies are a probe. By studying how they form, behave, and cluster, astronomers can test their models of dark matter and structure formation in the most demanding environment. Standard cosmology says voids should be the easiest places to predict because there is so little stuff in them. The void dwarfs are demanding more careful explanations. Some researchers have proposed that the dwarfs are not as isolated as they look. They may be linked by faint dark matter filaments that thread even through the voids, providing tiny pathways for galaxies to form. Others suggest that the early universe was more turbulent than the standard story allows, and that more dwarf-sized seeds survived in the underdense regions than expected. Still others argue that the count of void dwarfs is itself a clue that current dark matter models need adjusting. What none of them can do yet is dismiss the void dwarfs as flukes. They are real. They are numerous. They form a low-density ecosystem of tiny galaxies inside the universe's biggest empty rooms. The presence of these isolated dwarfs makes the voids feel more haunted than empty. Far from being silent, they may be quietly lit by faint, scattered worlds, each one a possible home for stars and planets nobody on Earth will ever see. The largest of these empty rooms, however, is not the Borealis void. There is another, even more vast, in a quiet part of the northern sky. In the constellation of Canes Venatici, the hunting dogs, the night sky looks ordinary to a casual observer. A few faint stars, some distant galaxies, nothing that catches the eye. Behind that gentle view, hidden by distance, is one of the largest known voids in the universe. This region was identified in surveys that mapped galaxy distributions across hundreds of millions of light-years. Where the data should have shown clusters and filaments, it showed a vast emptiness instead. Estimates of its size vary, but the most cited figures place it at over 1 billion light-years across, possibly larger. By volume, it dwarfs the Borealis void by a wide margin. By emptiness, it rivals or exceeds anything else in the catalogue. Its discovery added to a growing list of supervoids. These are voids so large that they begin to challenge the rules of how structure forms in the universe. Standard cosmology predicts that voids exist and predicts a typical range of sizes. The supervoids sit beyond the upper edge of that range. They are bigger than the models comfortably allow. A void this large has consequences. Light passing through it loses energy across the integrated Sachs-Wolf effect, leaving subtle imprints on the cosmic microwave background. Galaxies on its rim are pushed outward by the void's growing emptiness, contributing to the strange flow patterns of nearby cosmic neighborhoods. Even the way distant quasars look to our telescopes is slightly altered when their light has to cross such a vast underdense region. What makes this supervoid more unsettling is how quiet it is. There are no obvious bright signatures to mark it, no glowing clouds, no famous galaxy clusters on its borders that the public has heard of. It hides in plain sight behind the everyday light of nearby stars, only revealed when astronomers built a 3-dimensional map of the cosmos and realized that an entire region had almost nothing in it. Picture an old library, endless rows of shelves filled with books. As you walk down the aisles, every shelf is packed. Then you turn a corner, and a single hallway stretches into the dark. The shelves there are bare, long stretches of empty wood, with maybe 1 or 2 stray volumes leaning against each other. You keep walking, expecting the books to return. They do not. The hallway just keeps going. That is the feeling of stepping into the Cain's Venatici supervoid, scaled up by mind-bending amounts. This void also forces a rethink of timescales. To clear out so much matter from such a huge region, gravity needs time. The standard model suggests that voids of this size are pressing the limits of what can form within the age of the universe. Either the universe has been remarkably efficient at hollowing out giant rooms, or our models are missing something about how void growth works. Astronomers continue to study this supervoid as a kind of stress test for cosmology. It is one of several enormous structures that, taken together, suggest the universe is lumpier on extreme scales than the simplest theories predicted. Another such structure, the Sloan Great Wall, is partly defined by its proximity to a similar emptiness. The cosmic web at the largest scales is not a gentle pattern. It is a foam of titanic bubbles and titanic walls, a few of them too big for comfort. Yet inside these supervoids, the few galaxies that exist are doing something strange. They are spinning more slowly than they should. Galaxies spin. Their disks rotate around the galactic center, with stars circling at speeds that depend on how much mass is pulling them inward. By measuring the speed of rotation at different distances from the center, astronomers can estimate how much matter, both visible and dark, holds the galaxy together. That measurement has shaped modern cosmology. It is part of how the existence of dark matter was first inferred. Galaxies rotate too fast at their outskirts to be held together by visible matter alone. Something else, something invisible, must be providing the extra gravity. Dark matter halos became the default explanation, and they have been one of the cornerstones of cosmology ever since. Inside voids, however, the rotation story changes. Studies of void galaxies have found that, on average, they tend to rotate more slowly at their edges than galaxies of similar size in denser regions. The difference is not enormous, but it is measurable, and it persists across many surveys. Void galaxies behave as if their dark matter halos are smaller, less massive, or arranged differently than those of cluster galaxies. Several explanations have been proposed. One idea is that galaxies inside voids form with smaller halos to begin with. Without the constant gravitational nudging of larger neighbors, they are not pulled into the same kind of merger history that builds up massive halos in clusters. Their growth is more limited. They end up with less hidden mass and slower rotation curves. Another idea is that the dark matter inside voids may be distributed more diffusely. In dense regions, halos pack closely together. In voids, the same total amount of dark matter would be spread thinner. Galaxies in those regions would still have halos, but the gravitational pull at large radii would fall off faster, leading to slower rotation at the outskirts. A third, more provocative idea is that void measurements are giving us a cleaner look at how galaxies actually behave. Without the noise of nearby clusters and constant interactions, void galaxies are a kind of quiet laboratory. Some researchers think that small but persistent discrepancies between the standard dark matter model and observed rotation curves might show up most clearly in voids. Picture two rivers carving paths through a landscape. One flows through a busy region full of hills and other rivers, where the water is constantly redirected and stirred up. The other flows through a wide, flat plain, with no obstacles for hundreds of miles. The first river's behavior reflects everything around it. The second river reflects mostly itself. Void galaxies are like that second river. Their motions are less polluted by environmental effects, and that purity is why slight oddities in their rotation are so interesting. There is a stranger angle. Some studies have found that not only do void galaxies rotate more slowly, they also tend to align their spin axes in patterns that match the geometry of the void itself. Their rotation seems to know about the larger structure they live inside. The exact mechanism is not fully understood, but it suggests that voids and the galaxies within them are gravitationally connected in ways that go beyond simple density effects. This means voids are not just passive containers, they actively shape the small galaxies within them, all the way down to how those galaxies spin. That shaping has consequences for life itself. A galaxy that forms slowly, in isolation, with a thinner dark matter halo, may also be a galaxy without the brutal interruptions that elsewhere sterilize entire star systems. A void could be the safest place in the universe, or the loneliest. Imagine a civilization born in a galaxy at the heart of a deep void. Their planet, orbits a stable star, their continents form, their oceans give rise to life. After billions of years, they stand at the same threshold humans now stand at, looking up at the night sky and asking what is out there. Their answer would be very different from ours. When humans look up, we see the band of the Milky Way stretched across the sky. Beyond that, with even modest telescopes, we can spot Andromeda and other nearby galaxies. With slightly stronger instruments, we see thousands. With our best instruments, we see hundreds of billions. The universe, from our vantage point, is loud with structure. A civilization inside a deep void would see almost none of this. Their own galaxy would still arc overhead, of course. Their local stars would form constellations. But beyond the edge of their galaxy, the sky would be a wall of black. The nearest neighboring galaxy might be tens of millions of light years away, far beyond what their early telescopes could resolve. For most of their scientific history, they might honestly conclude that their galaxy was the entire universe. This is more than a thought experiment, it is a real cosmological problem. Some philosophers and physicists have written about what they call the cosmological imagination handicap. Civilizations in dense regions, like ours, get constant clues about the larger structure of reality. Civilizations in voids do not. Their ability to figure out the truth about the cosmos would be permanently impaired by where they live. Consider what this means for their physics. Without easy observations of distant galaxies, they could not measure the expansion of the universe by the same methods we use. Without seeing many other galaxies, they could not develop the cosmic distance ladder. Without distant supernovae to compare across galaxies, they could not detect dark energy. Without observable cosmic microwave background patterns, they might still find the radiation, but interpreting it would be harder. Their cosmology would be shrunken, incomplete, possibly even fundamentally wrong, and they might never know it. Picture growing up in a cabin in the middle of an endless white desert. No roads, no other buildings, no people. From the cabin window, every direction looks the same. You might invent stories about what lies beyond, but you would have no way to test them. Eventually, you might give up and decide the white desert is everything. Now imagine that the white desert is, in some sense, fooling you. Far beyond the horizon, there are mountains, rivers, cities, oceans. You will never see them. The void civilization lives in that cabin. There is a darker layer to this. As the universe expands, voids grow. Galaxies on the rims of voids are pushed farther away from each other. Distant galaxies redshift away over time, eventually moving beyond the visible horizon. For civilizations inside voids, this process is faster. Their already distant neighbors will fade from view sooner. The void civilization is on a one-way path toward more isolation, not less. In the deep future, every void civilization in the universe will see a sky that is essentially empty except for their own home galaxy. Their cosmology will collapse to a single galaxy story with no evidence that anything else exists. That fate raises a haunting question. Are voids quietly growing in ways that will reshape every other patch of the universe along with them? The cosmic web is not static. The web is alive, in a slow, gravity-driven way, and the voids are some of the most dynamic features inside it. Voids grow. They expand outward over cosmic time, fueled in part by the relentless push of dark energy, and in part by the steady flow of matter from underdense regions into denser ones. Every billion years, the average void widens. Every billion years, the walls between voids thin out a little more. When voids grow large enough, they collide. Their walls press against each other, and the matter between them gets squeezed. Eventually, the wall breaks. The two voids merge into a single larger void. The galaxies that once sat in the wall between them are now stranded inside the new combined emptiness, sometimes ending up far from any neighbor. This process is similar to what happens in a foam of soap bubbles. Small bubbles drift, grow, and eventually merge with their neighbors to form fewer, larger bubbles. The total volume of the foam stays roughly the same, but its structure simplifies. The cosmic web works the same way over billions of years. Computer simulations of this evolution are striking to watch. Tiny voids appear early in the universe, scattered throughout the cosmic foam. Over time, they grow, they merge, they consume each other. The cosmic web steadily becomes a network of fewer, larger voids, surrounded by sparser walls. The bright threads thin out, the dark spaces dominate. The implications for the future are heavy. If the trend continues, the cosmic web will eventually evolve into a small number of titanic voids, each one larger than anything we currently catalogue. Galaxies will exist mostly along the rims, separated by oceans of nothing. The universe of the deep future will look much emptier than the universe of today, even though the same amount of matter is still in it. Picture a foam in a bathtub, slowly settling over hours. At first, there are countless small bubbles packed together in a complex froth. As time passes, the small bubbles pop or merge. The remaining bubbles grow. Eventually, only a few enormous bubbles remain, with thin films of soapy water stretched between them. That is the long-term fate of the cosmic foam in slow motion. There is something unsettling about realizing that the universe is moving in this direction. Our familiar picture of galaxies, clusters, and threads is a snapshot. Future cosmologists, billions of years from now, would see a sparser, simpler structure. Past cosmologists, if any had existed in the early universe, would have seen a denser, more tangled web. We sit in the middle of an evolution that is still unfolding. Some researchers have begun to study void mergers in detail, looking for evidence of recent void collisions. The walls between merging voids leave specific patterns in galaxy distributions, and these patterns can be detected in modern surveys. The cosmic foam, in other words, is not just a metaphor. It is a measurable structure that astronomers can chart, and its history can be reconstructed. The evidence for void mergers also tells a quieter story. The cosmic web that we see today has already lost much of its earlier complexity. Many of the smaller voids that once existed have already merged into the larger ones we now study. The supervoids, with their billion light-year diameters, are partly the result of these mergers across deep time. That brings us to one of the largest single structures ever identified, a galaxy wall so massive it sits like a continent against the most extreme emptiness yet found. In 2003, a team analyzing data from the Sloan Digital Sky Survey announced the discovery of a structure so large it briefly held the record for the largest known object in the universe. They called it the Sloan Great Wall. The Sloan Great Wall is a vast sheet of galaxies, roughly 1.4 billion light-years long. It contains thousands of galaxies and dozens of clusters, all loosely connected along a single curving filament of the cosmic web. To get a sense of its scale, the entire local group, the small collection of galaxies that includes our Milky Way and Andromeda, is barely a footnote inside it. What makes the Sloan Great Wall most striking is what sits next to it. On one side of the wall lies a massive void, an underdense region nearly as long as the wall itself. The contrast is severe. On one side, an enormous concentration of matter, on the other, a vast emptiness. The Sloan Great Wall exists in part because of that void. The matter that should have filled the void was instead pulled gravitationally into the wall, leaving the void emptier and the wall denser than either would have been alone. This relationship is fundamental to the cosmic web. Every wall is matched with at least one void. Every void shapes the walls around it. The two features are inseparable. You cannot have one without the other, and they grow together over cosmic time, with matter draining from voids into the surrounding structures. Picture a coastline where a deep canyon meets a tall cliff. The canyon is impressive. The cliff is impressive. Together, the contrast between them is what makes the landscape extreme. Take away one, and the other becomes ordinary. The Sloan Great Wall and its neighboring void are the canyon and cliff of the cosmic landscape. The wall itself is not a uniform structure. It is built from clusters and superclusters strung along a curving filament. Galaxies inside the wall experience strong gravitational interactions, frequent mergers, and rich star formation histories. The neighborhood is dense, busy, and active. It is the opposite of life inside a void. Astronomers have used the Sloan Great Wall to test their cosmological models. The size and density of such a structure pushes against the limits of what standard cosmology predicts should form within the age of the universe. Some calculations suggest that the Sloan Great Wall is on the borderline of statistical impossibility under simple models. Either the universe has produced an unusually large structure, or the models are missing something about how matter clumps on the largest scales. This is part of a recurring pattern in cosmology. The biggest known structures, including the Sloan Great Wall, the giant supervoids, and even larger structures like the Hercules Corona Borealis Great Wall, all sit at or beyond the upper end of what models comfortably predict. There is a quiet tension building between observation and theory. The universe has more huge structures than the simplest models expect. Some researchers have suggested that this might not be a flaw in the data, but a sign that the cosmic web evolves differently on the largest scales than current models capture. Others suggest that the early universe was simply more lumpy than we have been assuming, with seeds of structure that have grown into giants. Either way, walls and voids together form a cosmic landscape that is more dramatic than the standard picture allows. And inside the voids themselves, the dark matter that should govern their behavior may not be obeying the rules we have written for it. Dark matter is the invisible scaffolding of the universe. It outweighs ordinary matter by about 5-1, and it provides the gravitational structure that holds galaxies, clusters, and the cosmic web together. Without dark matter, galaxies would not have formed. Without dark matter, the cosmic web would not exist. What dark matter actually is, however, remains unknown. No experiment has directly detected a dark matter particle. We know it is there only because of its gravitational effects on visible matter and on light. The standard model of cosmology assumes that dark matter is cold and slow-moving, clumping under gravity to form the halos that galaxies live inside. Inside voids, the behavior of dark matter becomes especially interesting. If dark matter forms uniformly across the universe, voids should still contain some of it, just less than denser regions. Surveys of voids using gravitational lensing, the bending of light around mass, suggest this is largely the case. Voids contain dark matter, but at significantly reduced density. The walls and clusters around voids contain it at much higher concentrations. This pattern leads to questions that go to the heart of fundamental physics. Why does dark matter clump the way it does in voids? Is the distribution we see in voids consistent with the standard cold dark matter model, or does it favor alternative models? Some of the alternatives are exotic. Warm dark matter, in which dark matter particles are slightly faster moving and harder to clump on small scales, would predict slightly different void structures than cold dark matter. Self-interacting dark matter, in which dark matter particles can bump into each other rather than passing through, would also leave different fingerprints in voids. Modified gravity theories, which try to replace dark matter altogether by changing the laws of gravity, predict yet different patterns. Voids are an ideal testing ground for these ideas. In dense regions, the noise of complicated gravitational interactions makes it hard to isolate the behavior of dark matter alone. In voids, the system is simpler, less ordinary matter, less complex dynamics. The behavior of dark matter, whatever it is, has fewer things to hide behind. Picture trying to study the behavior of a single rare bird in two environments. In the first, the bird is surrounded by hundreds of other species, each making its own noise and movement. In the second, the bird is alone in a quiet valley. In the second environment, you can study it more clearly. Its calls, its flight patterns, its routines all stand out. Voids are the quiet valley for dark matter. Recent surveys, including measurements from the Dark Energy Survey and other large projects, have begun providing detailed maps of dark matter inside and around voids. Some of these measurements show small but persistent discrepancies with the standard model. The discrepancies are not yet large enough to overturn the model, but they are large enough to keep the search for alternatives active. There is also the puzzle of the void dwarfs from earlier in this story. Their existence and behavior strongly depend on what dark matter does in low-density regions. Different dark matter theories predict different numbers of void dwarfs, different rotation curves, and different distributions. The dwarfs are, in a sense, the test subjects, and their answers are still being collected. The voids, then, are not just empty rooms. They are laboratories. The deepest mysteries of physics, including the nature of the most abundant kind of matter in the universe, may end up being answered partly inside places that contain almost nothing at all. That is fitting in a strange way. The largest features in the cosmos are empty. The largest known structure, however, is not a void. It is something even harder to explain, a wall of galaxies so large that its very existence is a problem. In 2013, astronomers studying the distribution of gamma-ray bursts, the brightest explosions in the universe, noticed something extraordinary. The bursts seemed to cluster in a particular region of sky, in a way that suggested an enormous underlying structure of galaxies producing them. That structure became known as the Hercules Corona Borealis Great Wall. Estimates of its size are staggering. Some measurements put its length at roughly 10 billion light-years. To put that in perspective, the entire observable universe is about 93 billion light-years across in diameter, and structures at this scale should not have had time to form during the age of the universe. The Great Wall is, in some accounts, large enough to violate the standard cosmological assumption that the universe looks roughly the same in every direction on large scales. This assumption, called the cosmological principle, is one of the foundations of modern cosmology. It says that on scales larger than a few hundred million light-years, matter should be distributed evenly. The Sloan Great Wall already pushes that limit. The Hercules Corona Borealis Great Wall blasts past it. If the structure is real, it suggests that either the universe contains far larger structures than current models allow, or our understanding of how matter clumps over time is significantly off, or the gamma-ray burst clustering is being misinterpreted as a single connected wall when it is really a collection of separate, unrelated events. The debate is alive. Some researchers argue that the Great Wall is a statistical artifact, the result of incomplete sky coverage and biased sampling. Others argue that even with corrections for those biases, the clustering remains too strong to ignore. New data continues to come in, and the question has not been settled. What is striking is the pattern this fits into. The Sloan Great Wall, the giant supervoids, the Hercules Corona Borealis Great Wall, even the KBC void with our galaxy near its center, all hint that the universe contains structures at the largest scales that are bigger or more extreme than the simplest models predict. Either there is more lumpy structure on cosmic scales than standard cosmology comfortably allows, or our models need significant updates. Picture a map of a continent that looks roughly even from a distance. Forests, plains, mountains, all spread out in expected ways. Now zoom in, and you find a single mountain range that runs the entire length of the continent, far larger than anything geology predicts. Then a desert that covers a third of the surface. Then another mountain range. The map starts to feel like it was built by a different process than the one your textbook described. That is the situation modern cosmology is quietly facing. The Hercules Corona Borealis Great Wall is the most extreme entry in this pattern. If it holds up under further analysis, it would force a serious revision of cosmology. Even if it turns out to be partly an artifact, the scale of the underlying structure that did produce the gamma-ray clustering is still hard to explain by the simplest models. This is one of the unsettling truths about the modern picture of the universe. The largest features are at the edge of what theory can accommodate. The voids are the negative space inside that picture, and they are equally extreme. The voids do something else, though, that few people outside specialist circles know about. Inside their vast, empty interiors, certain physical conditions become extreme in their own right, including the conditions for accelerating particles to enormous energies. Cosmic rays are charged particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They strike Earth's atmosphere constantly, producing showers of secondary particles that physicists have studied for over a century. Some cosmic rays carry energies far beyond anything that can be produced in human-built particle accelerators. The most energetic cosmic rays remain a mystery. Their energies are so high that the standard sources, like supernovae and active galactic nuclei, struggle to explain them. Something in the universe is accelerating these particles to nearly impossible speeds, and astronomers have been searching for the source for decades. Cosmic voids may be part of the answer. Inside voids, magnetic fields are weak, density is low, particles entering a void can travel for vast distances without colliding with anything that might slow them down or scatter their trajectories. The geometry of voids, combined with their gentle, large-scale magnetic structures, can in some models act as a kind of natural particle accelerator. Charged particles drifting through the boundaries between voids and walls can be slowly accelerated by the changing fields, gaining energy over millions or billions of years. This idea is not yet fully accepted, but it has support in serious theoretical work. Some calculations suggest that the largest voids could contribute significantly to the population of ultra-high energy cosmic rays observed at Earth. The exact mechanisms involve subtle interactions between cosmic magnetic fields, plasma flows on the rims of voids, and the long, undisturbed journeys particles can take through empty space. Picture a marble rolling across a series of slight inclines. Each incline is gentle, Across thousands of inclines, however, the marble picks up speed. Now imagine that the inclines are not on a tabletop, but in space, made of slowly varying magnetic and gravitational fields, and the marble is a charged particle traveling for billions of years. The result is a particle moving with energies that no laboratory can match. The implications are striking. The most energetic events humans observe in the universe may be partly produced not by violent objects, but by quiet, empty regions. The voids, often imagined as dead and inactive, may be silently working as engines for some of the most extreme particles ever measured. There is more. The voids may also affect how cosmic rays travel from their sources to Earth. Particles produced in distant galaxies have to cross voids on their way to us. The weak magnetic fields inside voids do not deflect particles much, so cosmic rays cross those regions in nearly straight lines. By contrast, when cosmic rays cross dense filaments and clusters, they get scattered and slowed. This means that the cosmic rays we see at Earth are filtered by the cosmic web. Particles coming through voids retain more of their original direction and energy than those crossing dense regions. The cosmic web acts like a complicated optical system, with voids as transparent regions and clusters as scattering ones. Maps of cosmic ray arrivals can, in principle, reveal information about the cosmic web that is hard to obtain by other means. Astronomers and physicists are still working to combine the data. Direct measurements of voids from galaxy surveys, indirect measurements from cosmic ray observations, and theoretical models of acceleration mechanisms all need to fit together for the full picture to emerge. What is clear already is that voids are not mere absences. They are participants in some of the universe's most extreme processes. And the patterns inside them may even hint at something stranger, a possible alignment in the largest scales of the cosmos that some scientists have nicknamed the axis of evil. The cosmic microwave background is supposed to look the same in every direction. It is the leftover glow of the Big Bang, smoothed out by hundreds of thousands of years of expansion before being released. By the time it reaches us, it should be nearly uniform across the sky, with only tiny ripples representing the seeds of future structure. In the early 2000s, when high-resolution maps of the microwave background became available, something strange showed up. Certain large-scale features in the map seemed to align with each other in unexpected ways. The patterns appeared to share a preferred direction in the sky. This direction was nicknamed the axis of evil by physicists Kate Land and João Margejo, partly as a joke and partly because it suggested the universe had a special direction, something cosmology was not supposed to allow. The axis of evil is not a physical object. It is a statistical alignment in the cosmic microwave background data. The largest scale ripples in the background, instead of being random, seem to point in roughly the same direction. The chance of this happening by accident in a uniform universe is low, but not impossible. What does this have to do with voids? The axis of evil aligns in some analyses with the location of certain large voids and the broader distribution of cosmic structure. Some researchers have suggested that the alignment is partly an imprint of the integrated Sachs-Wolf effect, with the largest voids and clusters along that direction shifting the temperature of the microwave background just enough to create the alignment we see. In this view, the axis of evil is not evidence of a fundamentally tilted universe, but a fingerprint left by the cosmic web on the oldest light. Others remain unconvinced. The alignment is harder to explain fully by the standard contributions from voids alone. The strength of the effect, the persistence of the alignment across multiple modes, and the overall geometry of the pattern have continued to puzzle cosmologists. Some have suggested more exotic explanations, including primordial physics that briefly broke the symmetry of the universe before inflation washed it out. Picture a vast, smooth pond. You expect ripples on its surface to be random, going in every direction. Instead, you notice that most of the largest ripples are oriented along a single line. There are smaller ripples in every direction, but the big ones share a preferred axis. You might wonder whether the wind blows mostly along that line, or whether the pond has a hidden shape under the surface, or whether you are simply misreading a small sample as a pattern. The cosmic axis of evil sits in that uncomfortable space between coincidence and signal. What makes the topic so interesting is its potential connection to voids. If giant voids are partly responsible for the alignment, then the cosmic web is leaving a stronger fingerprint on the universe than expected. If voids are not responsible, the alignment becomes more mysterious, hinting at something deeper in the early universe. This is one of the active frontiers of modern cosmology. New surveys, including the Dark Energy Spectroscopic Instrument, the Euclid mission, and the upcoming Vera Rubin Observatory, will produce far more detailed maps of voids and the cosmic web. Combined with refined microwave background measurements, those maps may finally settle whether the axis of evil is a real anomaly or a statistical illusion shaped by the largest empty regions in the cosmos. The voids, in other words, may carry the answer to one of the most stubborn puzzles about the geometry of the universe. They may also carry the answer to a more personal question. What would it actually be like to stand inside one, looking out at the night sky? Imagine being placed on a planet at the very heart of a deep cosmic void. The planet orbits a stable star. The star sits in a small, isolated galaxy, one of the few galaxies in this enormous empty region. You step outside on a clear night, look up, and try to make sense of what you see. The first thing that strikes you is the silence of the sky. There is no bright band of the Milky Way arching overhead because your galaxy is small and dim compared to ours. There are stars, but fewer of them than the dense skies of Earth. Constellations, if you trace them, are sparser, with longer gaps between bright points. Beyond the local stars, the sky is almost completely black. There is no Andromeda galaxy hanging like a bright smudge. There are no Magellanic clouds visible to the unaided eye. There are no nearby galaxy clusters glowing with the light of thousands of suns. There is nothing for as far as your eyes or even your earliest telescopes can see. Just darkness, more darkness, and a few scattered local stars. Your earliest astronomers, working with simple optics, would conclude that your galaxy was the entire universe. There would be nothing in their observations to suggest otherwise. The sky offers no hints. The stars they see are the stars of their own galaxy. Beyond that, blackness. If your civilization developed more advanced telescopes, the picture would only barely change. With great effort, your astronomers might pick out faint, distant smudges of light, the nearest neighbor galaxies on the far side of the void. The smudges would be tens or hundreds of millions of light years away, far beyond what could be resolved into recognizable galaxies for a long time. Even when their nature was finally understood, the number of visible galaxies from your vantage point would be tiny compared to what humans see from Earth. The cosmic microwave background would still surround your civilization, the same as ours. With sensitive instruments, your astronomers would still find the faint glow from the Big Bang. But interpreting it correctly would be much harder without the dense web of nearby galaxies to compare it to. Your cosmology would be limited by the geometry of your home. Picture standing in the middle of a vast, dark plain. The plain is so flat and so featureless that no matter how far you walk, the horizon never changes. There are a few small stones near your feet. Beyond them, nothing visible. You might come to believe eventually that the plain is the whole world. You would not be entirely wrong from your point of view. You simply have no way of seeing anything else. This is the quiet horror of life inside a deep void. The cosmos is full of structure, full of stars, full of galaxies, full of stories. From inside a void, almost none of it is reachable. Civilization's natural curiosity about the universe would be perpetually frustrated, not because the universe is hostile, but because the void hides the rest of it from view. Some cosmologists have used this imagined viewpoint to argue that we, on Earth, are unusually lucky. Our location near a moderately dense region, with bright nearby galaxies, gives us a clear window into the universe. A void civilization would not have that window. Their understanding of reality would be limited, not by intelligence or curiosity, but by address. That same line of thinking has led to a darker, deeper question. The largest void anomaly we have ever found, the cold spot, has refused to be fully explained. Some researchers have wondered whether its strangeness might point to something the standard story cannot accommodate. The cold spot in Eridanus, mentioned earlier, is one of the deepest mysteries in modern cosmology. The Eridanus supervoid sitting in front of it explains some, but not all, of its temperature dip. The remainder is still unaccounted for. That gap has invited some of the most exotic explanations in physics, including ideas that touch on multiverses and even on advanced civilizations. This is where the discussion turns speculative. The mainstream view is that the cold spot is most likely a statistical fluctuation, possibly amplified by the supervoid in front of it, and that no exotic explanation is needed yet. Most cosmologists prefer this conservative interpretation. The data does not yet force them to reach further. Some researchers, however, have explored more dramatic possibilities. One published idea is that the cold spot could be the imprint of a bubble universe collision, as discussed earlier in this script. Another, much more controversial idea has occasionally appeared in the popular science discussion. It is the suggestion that a civilization vastly more advanced than our own might be using regions of space for purposes we cannot yet imagine, leaving signatures we are only beginning to detect. This idea is not standard cosmology. It is a fringe hypothesis, raised mostly to test the limits of explanation. The reasoning goes like this. If a civilization existed at a high enough level, it might be able to manipulate matter and energy on cosmic scales. The largest features in the universe, including supervoids and unusual patches of the microwave background, could in principle be markers of such activity. Without other evidence, this remains speculation. Cosmologists raise it only as one of many extreme possibilities, not as a serious prediction. Why bring it up at all? Because the cold spot itself stubbornly refuses to be fully explained by any one standard cause. The supervoid in front of it is large, but probably not large enough on its own. The integrated Sachs-Wolf effect contributes, but probably not enough either. Statistical fluctuation remains a viable explanation, but the probability is low. When all the standard explanations leave a gap, exotic ideas inevitably crowd in. Picture a courtroom where every standard suspect has been ruled out. Investigators examine the evidence, eliminate the usual candidates one by one, and find that there is still a clue left over. The clue does not match any of the people in the standard pool. At that point, more unusual hypotheses begin to be considered. The investigators are not abandoning logic, they are extending it. The cold spot is a clue without a clear match yet. Future data, including more detailed maps of the cosmic web, deeper surveys of the supervoid, and better measurements of the microwave background polarization, should eventually pin down the explanation. Most likely, the answer will be a combination of natural cosmological effects that finally add up to the full temperature dip. But until that case is closed, the strange explanations will remain on the edge of the discussion. What makes this story relevant to voids in general is the lesson behind it. Voids are not just empty rooms. They are scientific frontiers. The biggest among them are connected to some of the deepest mysteries of cosmology, from the Hubble tension to the axis of evil to the cold spot. Each new survey reveals more of their behavior, and each new discovery raises more questions than it answers. The most personal of those questions, however, is closer to home. Some of the data hints that our own galaxy is being pushed in a particular direction by the cosmic web, and the destination may be unsettling. The Milky Way is not stationary. It is being pulled and pushed by the gravitational forces of the cosmic web around it. Some of those forces come from nearby clusters and superclusters. Others come from emptiness itself. By measuring the motion of the Milky Way and our nearby galaxies relative to the cosmic microwave background, astronomers can determine the net direction in which we are moving. The result is striking. We are heading toward a region of space called the Great Attractor, an enormous concentration of galaxies hidden behind the dust of our own galaxy. We are also being drawn toward an even larger structure beyond the Great Attractor, called the Shapley supercluster. But that is not the entire story. Some of our motion, it turns out, is not from being pulled by something. It is from being pushed by something. Or more precisely, by something not being there. In 2017, a team led by Yehuda Hoffman published research describing what they called the dipole repeller. This is a vast underdense region, a void located on the opposite side of the sky from the Great Attractor. Its lack of matter creates a kind of negative pressure on our galaxy. Surrounding regions pull more strongly than the dipole repeller does, so the net effect is that our galaxy is pushed away from the void. Roughly half of our galaxy's motion through the cosmic web can be attributed to this void on the other side. The dipole repeller is, in a sense, half of the reason we are heading where we are. This is a strange thing to absorb. Our galaxy's destination is being decided by both somethings and nothings. The Great Attractor and the Shapley supercluster pull us forward. The dipole repeller pushes us forward by being empty. Without either side of this equation, our motion would be different. Picture standing on a sled at the top of a long hill. There is a hill rising in front of you that you would naturally roll toward. there is also a sudden drop behind you, a deep valley with nothing solid in it. The combination of the slope ahead and the emptiness behind shapes your speed and direction. You are not just being pulled forward, you are being shoved forward, in part, by the absence of anything holding you back. That is the geometry of our motion through the universe. What this means is that voids are active partners in cosmic flow. They are not passive. They participate in shaping where galaxies go, how clusters grow, and how the cosmic web evolves. Every time a void deepens or expands, the gravitational landscape shifts, and the galaxies around it adjust their motions accordingly. This also has implications for our long-term cosmic future. Although the Milky Way is currently being pulled and pushed toward distant attractors, the expansion of the universe will eventually overcome these motions. In the deep future, all those attractive forces will be overwhelmed by dark energy. We will not actually reach the great attractor. We will not actually fall into the Shapley supercluster. Long before any of that, the universe's accelerating expansion will isolate us from those distant structures entirely. But for now, in this cosmic moment, we are being shaped by both fullness and emptiness in equal measure. The voids, far from being silent observers, are shoving us through the universe. That brings us back to a deeper unease. The presence of these voids, especially the largest ones, has begun to expose cracks in our standard picture of the cosmos. For decades, modern cosmology has been built on a model called lambda cold dark matter. It has been wildly successful, predicting everything from the patterns in the cosmic microwave background to the large-scale distribution of galaxies. It has handled the existence of dark matter and dark energy, the formation of the cosmic web, and the broad shape of cosmic history. In recent years, however, a series of small discrepancies has begun to add up. Voids have played a quiet, persistent role in many of them. Consider the pattern. The Hubble tension, the unresolved disagreement between local and distant measurements of the universe's expansion rate, may be partly explained by our living inside the KBC void. The integrated Sachs-Wolf effect from supervoids, including the Eridanus supervoid, accounts for only part of the cold spot, leaving an unexplained gap. The largest known structures in the cosmos, including the Sloan Great Wall and the Hercules Corona Borealis Great Wall, push against the limits of what standard cosmology can produce within the age of the universe. Void galaxies show subtle rotation oddities. The axis of evil shows faint alignments. Dark matter behaves in voids in ways that are not fully predicted by the simplest models. None of these problems is a smoking gun on its own. Each can be explained, sometimes with effort, by adjusting standard parameters or invoking statistical fluctuations. Together, however, they form a pattern. Each anomaly is consistent with the idea that the universe is more lumpy, more structured, and more strange on the largest scales than the standard model assumes. Picture a clock that runs perfectly for years. Then you start to notice that it gains a few seconds every week. Then you find that a small pinion is wearing unevenly. Then you discover a faint sound from inside that you cannot identify. Each problem alone is minor. Together, they hint that the clock's design might need a serious review. That is the situation modern cosmology is quietly facing. Some researchers argue that we are on the edge of a cosmological revolution. New instruments and surveys are about to provide vastly improved data on the cosmic web, including detailed maps of voids and walls. Those measurements will either resolve the tensions or confirm them. If the tensions hold up, the standard model will need to be modified. New physics may be required, possibly modified gravity, possibly new types of dark matter or dark energy, possibly entirely new ideas about how the early universe behaved. Other researchers are more cautious. They argue that the current tensions can still be accommodated within standard cosmology, with refinements rather than revolutions. They point out that anomalies have come and gone before, and that history shows the standard model has been remarkably resilient. Either way, voids sit at the center of the debate. They are the regions where many of the anomalies first appeared. They are the natural laboratories for testing alternative theories. They are the parts of the universe where the smallest deviations from standard behavior become detectable, because the noise of complex environments is removed. It is a strange thing to realize that some of the most important questions in physics may be answered by studying empty space. The cosmos has hidden its biggest puzzles in the places where there is the least to see. That is one of the recurring lessons of cosmology. Every era of progress has come from looking at the universe in a way that was previously dismissed as uninteresting. The voids are no longer being dismissed, and one of them, deep on the far side of the sky, may already be revealing its secrets in ways that connect back to the most personal mystery of all, the structure of our own cosmic home. The dipole repeller mentioned earlier deserves a closer look. It is one of the most striking examples of how a vast emptiness can shape our cosmic motion, and its existence has clarified something many cosmologists had only vaguely suspected for decades. The story begins with the puzzle of peculiar velocities. Our galaxy is not just moving away from other galaxies because of the universe's overall expansion. It is also drifting through the local cosmic web at a measurable speed in a specific direction. By comparing our motion with the perfectly steady reference frame of the cosmic microwave background, astronomers can pin down both the speed and the direction of this drift with high precision. For a long time, the Great Attractor was thought to be the main driver. It is a real concentration of galaxies, hidden behind the dust of our own Milky Way, pulling us toward it. Yet the math never quite worked out. The Great Attractor's gravity was not strong enough on its own to fully explain our motion. Something else had to be involved. Then came the Shapley supercluster, an even larger structure beyond the Great Attractor. Adding it to the calculations helped, but a residual motion remained. There was still an extra component pointing in a specific direction that no known structure quite explained. Yehuda Hoffman and his colleagues approached the problem from a different angle. Rather than searching for more attractors, they mapped the cosmic flow patterns in detail and identified a region on the opposite side of the sky from the Great Attractor that had unusually little matter. The region was so empty that its absence of gravity relative to the surrounding cosmic web was effectively pushing our galaxy away. This was the dipole repeller, not a new attractor, but an underdense region that, by being empty, contributed to our motion just as much as the densest superclusters did. The naming captures the geometry. We are caught in a dipole pattern with attractors on one side and a repelling void on the other. Picture standing on a giant trampoline. On one side of you, several heavy bowling balls have been placed close together, creating deep dips that pull you toward them. On the other side, the surface is unusually flat and high, with no weight at all. You will naturally slide toward the bowling balls. Part of that slide, however, comes from the lack of weight on the empty side. If something was sitting there, it would balance the pull. With nothing there, the balance is broken, and you accelerate. The dipole repeller is the empty side of the trampoline. Its absence shapes our motion just as much as the presence of distant attractors does. The discovery has practical and conceptual consequences. Practically, it allows astronomers to fully account for the Milky Way's motion through the cosmic web for the first time. The combination of the Great Attractor, the Shapley supercluster, and the dipole repeller produces a model that matches observations cleanly. Conceptually, it reinforces the lesson that voids are active. They participate in cosmic dynamics. They are part of the gravitational landscape, even though they contain almost nothing. There is also a deeper unease in the picture. The dipole repeller reminds us that emptiness itself is a force. It influences where galaxies go. It influences where we go. It influences the structure of the cosmic web at the largest scales. Every cubic light-year of empty space is, in a real sense, doing something. It is shaping the matter around it. That truth applies even to the smallest scales. Inside the deepest voids, the very fabric of space, the quantum vacuum, behaves in ways that are still poorly understood. Empty space is not really empty. Even in a perfect vacuum with no atoms, no light, and no fields above the lowest possible level, the laws of quantum mechanics insist that fluctuations are constantly happening. Pairs of virtual particles flicker in and out of existence. Energy ripples through the underlying field structure. The vacuum, at the smallest scales, is a frothing sea. This is not speculation. The effects of quantum vacuum fluctuations have been measured in laboratories. The Casimir effect, the Lamb shift in atomic energy levels, and aspects of the cosmological constant problem all involve the energy of the vacuum. The vacuum is real, and its dynamics are real, even when no obvious particles are present. Inside a cosmic void, the situation becomes especially interesting. The voids are the closest thing the natural universe offers to an idealized vacuum. Density of ordinary matter is very low. Magnetic fields are weak. The temperature of intergalactic gas in many parts of the void interior is quite cold. The contributions to the local environment are minimized in a way that is almost impossible to replicate in any laboratory. Inside such a region, the quantum vacuum dominates. The vast majority of the energy in a deep void may not come from atoms or light at all. It may come from the underlying vacuum itself. This connects to one of the deepest puzzles in physics, the cosmological constant problem. When physicists try to estimate the energy density of the vacuum from quantum field theory, the predicted value is enormous, far larger than what is actually measured. The mismatch is one of the biggest open questions in fundamental physics. The vacuum, in theory, should have far more energy than it appears to have. Something is cancelling out almost all of it, and nobody knows what. Voids are an environment where this mismatch becomes most relevant. They are the places where the vacuum is most directly visible, with the fewest distractions from ordinary matter. If new physics is hiding in the vacuum, the voids may be where its fingerprints are easiest to find. Picture an immense, silent room. The walls are perfectly insulated. The air is pumped out, the lights are off. To any human sense, the room is empty, but on a microscopic level, the floor of the room is buzzing with activity. The vacuum below the visible scale is alive, bubbling with virtual events, even when nothing is there in the traditional sense. That is the cosmic void, scaled up by enormous factors. Empty by every conventional measure, full of subtle quantum dynamics underneath. This idea has consequences for cosmology. The energy of the vacuum, whatever it really is the primary driver of dark energy, the force expanding voids, and the cosmic web. The vacuum and the voids are intimately connected. Understanding one means understanding the other. Future research into voids may directly inform our understanding of vacuum energy, dark energy, and the long-term fate of the universe. There is another, stranger thought. Some theories propose that the vacuum can have multiple stable states, and that a transition from one state to another could in principle propagate across the universe at nearly the speed of light. Such a transition would change the laws of physics behind it, with catastrophic consequences for any matter it encountered. The probability of this happening is, according to current models, extremely low and not worth losing sleep over. But the conditions inside deep voids, with minimal interference from matter, are theoretically the cleanest places for the vacuum to exist in its current state. They are the purest preserves of the laws we know. What remains then is to ask what happens to the rare matter that ends up stranded inside such an environment. The galaxies and gas that drift in voids face a peculiar fate. A galaxy inside a deep void is, in many ways, abandoned. It has no major neighbors. It has no companion clusters. The cosmic web around it is busy elsewhere, drawing matter into walls and filaments. The void galaxy is alone, and as the universe expands, it grows more alone over time. What happens to such a galaxy across the long span of cosmic history? For a while, life inside the void galaxy continues much as in any other galaxy. Stars form, planets orbit, civilizations, if they exist, rise and fall on whatever timescale biology allows. The local activity does not depend on having neighbors. A galaxy can sustain its own internal evolution for billions of years on its own resources. Eventually, however, the resources run out. Star formation requires fresh gas. In dense regions of the cosmic web, galaxies can pull in new gas from filaments around them, replenishing their reserves. In voids, there is no nearby filament to draw from. The gas that the galaxy starts with is the gas it has. Once that fuel is consumed, no new generations of bright young stars will appear. The galaxy will fade slowly into a population of older, dimmer stars with no significant new births. Across cosmic time, this fading is dramatic. A void galaxy may remain visible for tens of billions of years, but its glow will steadily redden and dim. Its bright blue stars, the ones that mark active star formation, will exhaust themselves. Its remaining stars, mostly long-lived red dwarfs and aging giants, will continue to shine, but with a quieter, deeper light. Picture a small village in a remote valley, isolated by mountains. As long as the villagers have stored grain, they thrive. They build, they craft, they raise families. But no caravans bring new supplies. No traders pass through with fresh seeds or tools. Over generations, the stockpiles dwindle. The village does not collapse all at once. It simply becomes smaller, quieter, less colorful. The valley remains, but the life in it grows slower. That is the long history of a void galaxy. The matter inside that galaxy, however, does not disappear. It remains where it is, gravitationally bound, slowly evolving. Over hundreds of billions of years, the stars will burn out one by one. Stellar remnants, white dwarfs, neutron stars, and stellar black holes will accumulate. The galaxy will become a graveyard of compact objects, drifting through the same patch of empty space, occasionally interacting with each other across enormous distances. The deep future is even stranger. Trillions of years from now, even the most long-lived stars will have died. The galaxy will be dark. The voids around it will have grown larger, swallowing more of the cosmic web. The galaxy will be a small island of frozen matter, inside a much larger, much darker emptiness. In some theoretical timelines, even the matter inside the galaxy may eventually decay, depending on whether protons remain stable on the longest scales. If protons do decay, after a vast time the galaxy's matter will disperse. If they do not, the galaxy will remain a frozen, dark structure for unimaginably long periods. Either way, the void becomes more dominant over time. The matter in voids, especially in galaxies abandoned far from any wall, faces a future of slow fading, isolation, and eventual silence. The voids are not just empty, they are patient. They wait. What that patience means at the larger scale is one of the most haunting predictions of modern cosmology. The long-term future of the universe is dominated by emptiness. This is not a poetic claim. It is the direct consequence of well-understood physics applied across enormous spans of time. Right now, the universe is in a phase where dark energy is steadily winning against gravity on the largest scales. Galaxies that are not gravitationally bound to each other are being pushed apart by the expansion of space, with the rate of expansion accelerating. Over hundreds of billions of years, this acceleration will isolate every galaxy cluster from every other galaxy cluster. The cosmic web that we currently see will fragment. Each isolated cluster will sit alone in an expanding ocean of darkness. The voids will grow. The walls between voids will thin. The clusters will become islands, smaller and farther apart from each other, surrounded by ever-widening emptiness. In about 150 billion years, give or take, most of the galaxies currently visible to us will have receded beyond what astronomers call the cosmic event horizon. Their light will redshift away into invisibility, never reaching any future observer in our part of the universe. To anyone looking up from a planet in our local cluster at that distant time, the sky beyond the local group of bound galaxies will be black. The voids will have, in effect, absorbed everything else. Then, on far longer timescales, even the bound clusters themselves will face their fates. Stars will burn out. Galaxies will fall apart through gradual gravitational interactions, ejecting most of their stars into intergalactic space. The remnants will eventually drift, and over inconceivable spans of time, even those drifting remnants may decay or evaporate, depending on the long-term behavior of matter and black holes. In the deepest future, the universe will be almost entirely empty. The voids will have won completely. The cosmic web will be a memory, encoded in the long-decayed light of structures that no longer exist. Picture the slow fade of a vast city at night. At first, the city is full of lights, block after block, neighborhood after neighborhood. The windows glow. Over generations, lights start to go out. Some buildings empty, some neighborhoods fade to black. As more lights go out, the dark areas grow, swallowing the city street by street. Eventually, only a few small pockets of light remain, scattered across an enormous black landscape. Then, even those go out. The city is still there in its ruins, but the lights are gone. That is the long arc of the cosmos. This is the fate the voids are pointing toward. They are not just current features. They are the dominant structure of the future. Every empty region that grows today is a sneak preview of what the universe will look like in much later eras. Studying voids is, in a real sense, studying the final form of reality. There is something humbling about this picture. The universe has been in its bright phase for a relatively short part of its possible history. The brilliant cosmic web that we see now, with its filaments and clusters and walls, is a transient feature. The long-term default state of the cosmos is emptiness, expansion, and silence. We are, in cosmic terms, watching from a balcony during the show. The fireworks are still going, the lights are still on, but the sky beyond the balcony is already growing darker than it once was, and it will grow darker still. Inside that darkening picture lies a final, unsettling possibility. The emptiness is not just spreading, it may be inevitable, a deeper truth about reality than the brightness ever was. Across this entire story, voids have been described in many forms. The local void at our cosmic doorstep, the Botus void with its single lonely island of galaxies, the KBC void that may quietly contain our entire galaxy, the supervoids carving out billion light-year regions, the dipole repeller pushing us through space, the vast empty future toward which all of cosmology seems to point. A pattern runs through every chapter. Voids are not the exception, they're becoming the rule. In the present moment, ordinary matter, dark matter, and the bright cosmic web feel central to our understanding of the universe. We name galaxies. We map clusters. We celebrate the structures that we can see. Yet by volume, the voids already dominate. The universe is mostly emptiness, with bright structures clinging to the edges of vast underdense bubbles. By energy, dark energy dominates, and dark energy is essentially the energy of the vacuum, the energy of emptiness itself. When you put these facts together, a strange picture emerges. The most abundant ingredient of the universe is emptiness, both in space and in energy. The most extensive structures are voids, not walls. The most important driver of cosmic evolution is the vacuum's tendency to expand, not the gravitational tendency of matter to clump. From this angle, the universe is mostly nothing. Mostly nothing is doing most of the work, and the emptiness is gaining ground over time. The universe began, as far as we can tell, in a hot, dense, almost uniform state. Matter was the protagonist. It cooled, clumped, and built galaxies, stars, and planets. For a time, the bright story dominated the cosmos. Now, however, the slower, deeper process of expansion is overtaking that story. The voids are widening, the walls are thinning, the cosmic web is fading. In the deepest future, the bright story will be over, and only emptiness will remain. Picture a great full hall, lit by countless lamps. The lamps shine for a long time. Eventually, however, the air conditioning of the building begins to dim them, one by one, in a slow, irreversible process. The hall is still standing. The walls are still painted, but the lamps grow steadily fewer, and the dark spaces grow steadily wider. Over enough time, the hall has only a few lamps left, and most of it is in shadow. Eventually, the last lamp goes out. The hall is then a vast, unlit interior. The structure remains, but the brightness is gone. That is the cosmic picture, scaled up by every imaginable factor. There is something profoundly humbling about contemplating this. The brightness of the night sky as humans have known it across history is a temporary feature of cosmic time. The crowded, lively, structured universe we see is a passing phase. The default state of reality, in cosmic terms, is emptiness, and the universe is steadily relaxing back toward that default. Yet for those of us alive now, the brightness is still here. The cosmic web is still glowing. The voids, vast as they are, have not yet swallowed the structure around them. We sit, in this moment, between the lit phase and the empty phase, watching both the past and the future unfold around us. The voids tell that story more clearly than any other cosmic feature. They are the negative spaces that define everything bright. They are the slow, quiet engines of cosmic isolation. They are, in a deep sense, what the universe is becoming. The most terrifying truth about empty space between galaxies is that it is not staying empty. It is growing. It is winning. And one day, far beyond any human horizon, it will be all there is.